Well, good afternoon or good morning, depending on where you are. So I'm going to talk to you today about composites and fatigue testing and predictive capabilities. So, in the past, I've heard people say that composite materials don't fatigue. Alas, this is not true. The photograph here of a wind turbine blade fatigue failure is one piece of evidence. We didn't have to go very far to get this. It was taken by one of my colleagues out of our office window. So in today's presentation, we are going to look at the phenomenon of composite fatigue and at some of the associated physical testing and analytical methods. So the agenda, very briefly, I'm going to give you a short introduction, talk about some different types of composite material and some of the trends that we see in industry. I'm going to follow up with that with a description of fatigue in composite materials. We're going to look at some of the physical testing aspects and at some of the methods that we're exploring to do with strength and fatigue calculations. So without further ado, into my introduction. First of all, I should just, you may notice that on our slides we have this name Prenscia appears, and some of you may be wondering what Prenscia is. What it is it's a division of HBM that has arisen by bringing together the software of nCode and ReliaSoft. I've come from the nCode side of things, and the fatigue of composites that we're talking about today is particularly relevant for the nCode DesignLife product. Okay, so let's talk about composites. In general, a composite is any material that has more than one constituent. So concrete, for instance, might be considered a composite material, or even some alloys such as grey cast iron, which have a mixture of phases. So that's a strict definition. However, what we're going to focus on today is what most people think about when we talk of a composite, and that is fibre reinforced plastics. Now, these type of materials tend to be particularly good for applications where a high stiffness or strength to weight ratio is required, and hence the increasing use of carbon fibre laminates in aerospace. So something like the Dreamliner, which has around 50% carbon fibre composite content, is a kind of prime example. But increasingly, we're also seeing interest and use of composite materials in automotive applications. Okay, so in this presentation we're going to be focusing on fibre reinforced materials. We can broadly classify these into two groups, which have either discontinuous fibres, or that's chopped fibres, or continuous. So discontinuous fibres, composites, can include materials with short fibres. So these are fibres that may be around 0.5 millimeters or less, often injection molded. So thermoplastics such as polyamides or polypropylenes with perhaps 30 or 50% of glass fibres are amongst the most common materials here. And these are, as I mentioned, tend to be injection molded. There's another class of material, though, with longer fibres, typically 25 or 30 millimeters. The fibres are commonly glass, but increasingly chopped carbon fibre tows are also used, and these are embedded in a thermosetting matrix, usually, such as a polyester resin or epoxy. So this type of material, you may have heard of sheet moulding compound or bulk moulding compound. Well, these types of material are typically made into shapes via a hot pressing operation, which shapes and cures it. So these types of discontinuous fibre material are very flexible in terms of the shapes you can produce, and not too expensive, but because the fibres are cut and not necessarily well aligned with the loading directions, you don't realise the full strength and durability potential of the fibre matrix combination. To achieve that, what you need is continuous fibre composites. And it's continuous fibre composites that's going to be the main focus of my presentation today. Now, some of these, for instance, unidirectional carbon fibre is fantastically strong. It has a static strength of often around 2,000 megapascals in the fibre direction. Unfortunately, it's also fantastically weak in other directions, which means that in order to make it usable, you have some work to do, and you have to sacrifice some of that outright strength to make it more robust to loadings in different directions. So you can do this by weaving it, which has the advantage that it also looks pretty, or by creating a laminate with layers with different orientations. So these types of material are much stronger than the chopped fibre composites, but you're also a bit more restricted. They're not so easy to shape, and they're more expensive to manufacture in terms of the time to assemble and cure each part. They normally have thermosetting matrices. Okay. Okay, so why are we interested in composites? Well, a lot of it's about weight. So take the automotive industry, for example. In the auto industry, there's a massive pressure from the US CAFE standards to reduce fuel consumption and CO2 emissions. And reducing weight is one of the key ways of achieving this. The table at the bottom shows the kind of fuel consumption improvements that can be made simply by cutting weight from a vehicle. So if we look at the right-hand side of the table here, we can see that if you can reduce a vehicle weight by 20%, you get about 7.6% improvement in fuel economy. However, if you go further and you take advantage of the loss in weight to downsize the engine and to get back to your original baseline performance, then you can get something closer to, you get around 16.5% cut in fuel consumption. So you can see that weight reduction is a key tool in improving the efficiency of vehicles, as well as improving performance and so on. So as a result of this, we're seeing a rather rapid increase in the use of composite materials. So if you look at the chart on the right here, you can see a projection of the expected growth in the consumption of carbon fibre over the next few years. And using composites does offer some other advantages as well. For instance, you can reduce the number of parts by developing more integrated structures by redesigning to use composites. However, there are some major drawbacks, particularly for the stronger materials, and particularly for the automotive industry, where they're really interested in short cycle times in production and low cost. And this is a real challenge for the higher strength composite materials. So there's a lot of work being done to get to a decent compromise between cost of production and strength for automotive particularly. Okay, so that was a brief introduction. Let's talk about fatigue. So this slide asks the question, is fatigue of composites a real issue? The short answer is yes. There might be some cases where the dimensioning of a design is controlled by the static strength and stiffness alone, so that to the extent that fatigue is not an issue, but otherwise it is a concern, and composite materials can and do fail by fatigue, and that is due to repeated or varying loads that are less than the static strength of the structure. So manufacturers therefore need to find ways of avoiding premature fatigue failure through analysis or testing, or both, and also ideally, but to optimize their designs by through analysis as well. So on this slide, we've got a few wind turbine and aerospace examples, including fuselage, wing, and engine. On the next slide has some automotive pictures, so increasingly used in automotive as well. They have to be durable under a wide variety of operating conditions, including high and low temperature and humidity. And these materials offer a lot of advantages, but unless we can really optimize their performance, which means understanding how long they're going to last, then you can't take full advantage of those beneficial properties. Okay, so let's just think a little bit about the fatigue process. I come originally from a metal fatigue background. So in metal fatigue, failure often occurs due to formation of often just a single crack or maybe a small number of cracks that coalesce. The process in composites can be rather more complicated. You can get a number of different types of damage occurring, depending on the matrix and the fibre material that you've got, depending on the strength of the interfaces between them, depending on the loading direction, and so on. So, for example, a UD, unidirectional laminar, loaded in tension, has a strength that's dominated by fibre breakage and is extremely strong. In compression, however, fibre buckling becomes very important, and because of that buckling, it's a lot stronger in tension than it is in compression. In a woven composite, you'll often find that damage starts with cracking between the fibres of the transverse toes. So this is cracking basically through the matrix. That can progress to delamination between the toes, increasing the stress, local stress concentrations until fibre breakage starts to occur. So you can get different types of material, different types of loading can generate different types of failure. And the mechanisms are complicated and may have a number of different processes interacting, depending on the material, on the layup, on the manufacturing process, and so on. Another feature of composite failures fatigue failures in practice is that they're often associated with features or defects that have been introduced during the manufacturing process. So these could be things like ply drop-offs, where you introduce a resin-rich or feed region. Fatigue can also interact with other types of damage. So, for instance, one of the things that aerospace manufacturers are very concerned with is what they call barely visible impact damage. So this could arise from a bird strike or somebody dropping a spanner on the wing. Damage from some impacts may be barely visible, but could grow under subsequent fatigue loading. Another big difference compared to metals is in metals, often the first sign that you've got a fatigue problem is that your component breaks into parts. That often doesn't happen in composites. In composites, they will often gradually lose stiffness due to an accumulation of micro cracks, fibre failures and delaminations, etc., which soften the component so that it becomes unusable sometimes before it actually separates into two parts. When it comes to analysis, fibre reinforced materials are typically inherently anisotropic and inhomogeneous, and that makes FE much more difficult, complicated. They can also be very sensitive to temperature. They're often operating close to or above the glass transition temperature of the matrix in some cases, particularly with thermoplastics. They're also sensitive to the environment. We've been doing quite a lot of work with short fibre reinforced polyamides, and they absorb moisture from the atmosphere, and in doing so may lose up to maybe 40% or so of their stiffness and strength. So environment and temperature are very important. Okay, so on this slide, I'm showing you some typical fatigue data for a unidirectional carbon epoxy material. So the data comes from coupon tests. The coupons are cut from plaques, and they're cut at different orientations compared to the fibre direction. So what we're looking at in the left-hand plot here is our SN curves for coupons where the coupons are cut parallel to the fibres, and coupons where they're cut transverse to the fibres, or 90 degrees. So if you look at the top curve, which is for the fibres that are aligned with the loading direction, we've got a fantastically high strength and fatigue strength. We have a UTS of around 2,000 megapascals and a very strong. It's very strong in fatigue. I should emphasise that these tests have been carried out at R equals 0.1. That is, they are tension fatigue tests. However, look now at the SN curve for the 90-degree orientation. That is this line, which is right down by the axis here. So I think you can see that in the 90-degree direction, we have a fantastically small static and fatigue strength. So this is why this type of material needs to be used in a multi-directional laminate. Because if you just use it in a unidirectional form, any slight loading off axis that's not in the direction of the fibres will give you very early failures. Another thing that's of interest here is the effect of mean stress. One of the classic ways of displaying fatigue data to understand the effect of mean stress is in the form of a Hague diagram. So these are plots of stress amplitude on the vertical axis, mean stress on the horizontal axis, and the lines are contours, the dotted line, fatigue life. They're sometimes known as a constant fatigue life diagram. Where the lines converge on the axes, these are the tensile strength and the compressive strength of the material. So this is what the top plot is for loading in the fibre direction, and you see that it's giving us good static and fatigue strength in tension, rather weaker, as I mentioned, in compression because of different mechanism. One of fibre buckling is having an influence here. However, if you go in the transverse direction, we find the reverse is true. The strengths are much lower. You know, there are it's a tiny fraction of the strength in the fibre direction, but in the transverse direction, it's very weak in the tension and much stronger in compression. Okay, so that's some typical data. Okay, that was just a kind of a quick overview of the phenomenon of fatigue in laminates. Let's look at now at some of the physical testing aspects of composites. Now, wherever anybody talks about testing composites, you're likely to see a diagram like this, which we might call the pyramid of testing. It provides, for instance, a good description of how the aerospace industry uses testing in such a way that they can put largely composite planes, such as the 787, into the air with a reasonable degree of confidence. So at the bottom of the test, bottom of the pyramid, you have coupon tests, and lots of them. So these can be used to provide fundamental material properties for building analysis models. You can also use these tests to study the effects of environment. You can to determine laminar and laminate properties, and how the laminate properties change with layup. So these will be coupon tests, and the aerospace industry will do lots and lots and lots of these. The second level up looks at a smaller number of tests now on features. These can be geometrical features such as holes or shaped sections, or could be joints between dissimilar materials, and these are known as sub-element tests. Generally, these things are still fairly small in scale. They're the sort of thing that you could test on a conventional uniaxial test frame, for example. And you can use this data to start validating your models, so comparing test data to basic FEA models using materials data that you've generated at the coupon level. So this kind of correlation is very important, as a lot of composite analytical techniques are still not all that great on making the transition across scales. Moving up the pyramid, the parts being tested get more complicated, larger, and they require much more bespoke testing rigs. So these are expensive. We do much less of them, and later in the process, typically on chosen designs. And at the top, you have the full-scale tests, which the aerospace industry still requires, which of course are hideously expensive, complicated, and time-consuming. That's the kind of pyramid of testing. I'm going to be thinking mainly about what goes on at the bottom level or two. So if you're working with a composite material and you're trying to understand how it might behave in service, this process starts with getting some baseline data on the UD or woven, or if you like, non-crimp fabrics that you're using to get the properties of the individual layers, and then building from there to try and understand the effect of the layup. Whatever that is, it's often quasi-isotropic in a lot of cases, and there's a number of considerations when you start to try and do testing that is relevant to your structures. So, for instance, you may have a particular layup in your coupons, but within a structure, particularly if there's some multiple curvature within it, the orientations on the between the fibres may have a continuous variation over the structure. There are a lot of other things that can have an influence on properties. For instance, the degree of cure. Curing can also leave significant residual stresses. You have to consider the condition that you're testing in, the temperature and humidity levels and moisture content of the composite can have a big effect on the properties. So if you're wanting to simulate in particular conditions, then you need to make sure that you're covering that. Then there's the issue of defects. Defects can include things like dry spots, inclusions, small delaminations, wrinkles, waviness of fibres. All these things can have a significant effect on the in-plane properties and particularly on the fatigue strength. And interfaces and so on are very important as well. So there's a lot of different considerations and that you may need to take into account to get relevant data for your particular cases. One of the other issues is another challenge is just getting good specimens and test methods. So making good composite specimens can be quite difficult. Most of them are made from flat panels. So first of all, you need to manufacture these panels, and from these the specimens can be machined, and usually we need to apply some kind of end tab to the specimen also in order to grip it. So it's important that you get where you're dealing with a UD material, that you get the fibres properly aligned. If you're testing specimens with wrinkles or waviness in them, particularly if that's not representative of what will occur in your manufactured parts, that's pretty undesirable. Even things like bonding the end tabs on can be a bit of a minefield. If you don't use the right kind of adhesive, sometimes the adhesive fatigues faster than the composite, so you just end up by losing the tabs. You have to consider what material the end tabs should be made of. Some people like to use aluminium end tabs, but this can cause issues, particularly when you're testing at non-ambient temperatures because of the differential thermal expansion. When it comes to testing, there are some testing standards. Some of them are useful, and other practices you might have to establish by trying them out yourself. So just to give you a couple of examples, when you want to load components into compression, that's really quite tricky because you often have to try and come up with some arrangement to avoid buckling, either by having much shorter specimens or by using some kind of anti-buckling guide. Other issues, loading frequency is very important. If you test at too high a frequency, you get self-heating. And there's there's always some variation between batches. From one plant to another, there may be some variations in volume fraction, for instance, and we need some way of understanding the variation, batch-to-batch variation. There's a lot of considerations to getting good test data and test data that you can rely on. So there's a few pictures on this slide that illustrate some of the challenges. On the top right, you've got some typical UD fatigue specimens. You can see these have been tested and broken. You can see from the way that they tend to crack in between the fibres, except for the one that's aligned with the loading direction. These have all been cut at different orientations. You can see the end tabs are on there. If you don't put end tabs on and you're testing this kind of material, they will pretty much always fail at the edge of the grips, and that's an invalid test. In some cases, you can use a dog bone sample or wasted specimen, such as this one on the bottom right. That's for a case where the fibres are oriented transverse to the specimen. You can't use this kind of geometry for a longitudinal specimen because it just splits parallel to the fibres, and these shoulders become in effect not part of the specimen. So that's all for in-plane properties. If you want out-of-plane properties, they can be a bit trickier. One way of doing this is by building up very thick specimens. So if you look at these chunky little black specimens here, these are built up from many layers of composite. But I think you might imagine that these are very difficult and expensive to make. They're not ideal. There are other ways of getting out of plane properties. Other challenges, test machine requirements. Composites, carbon fibre composites in particular, are very strong in the fibre direction and very weak in the transverse direction. So it's very difficult to test all your specimens on one rig. So for 0 degree UD unidirectional tests, you probably need a 100 kilonewton rig. That should be enough. But that won't really give you enough resolution for your 90 degree tests, which are very weak, and so you'd be better off doing that on a much smaller rig, such as a 5 kilonewton machine. However, when you then start to try and test laminates, so by the time you've put together a representative layup and made the coupon big enough to be truly representative of the material, you end up with a coupon that's really quite large, and you suddenly find that you might need a 250 kilonewton machine or more to break it. There's a lot of considerations. On top of that, you may need to test it in an environmental chamber, and you need to think about the extensometry as well, which can be difficult if you're testing in a chamber, or if you've got to fit anti-buckling guides. Okay, so that was just a quick review of some of the issues around testing. While we're talking about testing, I should of course mention our fatigue testing laboratory in Rotherham, the AMCT, which is focused mainly on providing fatigue properties for materials and structural joints for our customers for use in the software. However, as well as routine material characterization, we're increasingly involved with collaborative research with our customers with the aims of improving our products and services as well. Okay, so that's a little bit about testing. Let's now have a look at some of the analytical methods that we have for dealing with strength and fatigue of composite laminates. As I mentioned before, composite laminates can fail in a variety of mechanisms. So generally involving a combination of one or more of the following. So at the microscopic level, you may get fibre fracture, fibre buckling, splitting, debonding of fibres from the matrix, fibre pull-out, the matrix cracking. So these are all things that are going on within each layer. And then at the laminate level, we can also see macroscopic failures occurring, which may be more or less dominated by fibre failure or more or less dominated by matrix failures. Very often there is a very significant contribution from delamination when it comes to final failure. And one thing that's important to point out is that composites are often quite damage tolerant. So the fact that you have some failure at a micro scale within a lamina doesn't necessarily mean that you're going to see early failure in the laminate itself, in the overall structure. So what I'm going to do is to try and explain some of the techniques that are used for composites. I'm going to back up and just talk briefly about metals. So most metals can reasonably be treated as isotropic, and their strength is normally characterized by a uniaxial stress strain curve, just from a normal tensile test, from which we can derive the yield point at which the curve still starts to go non-linear, and the UTS, the ultimate strength. And typically the behaviour is linear elastic up to the yield strength. So we have this yield point here, which is the important material parameter. When it comes to adding in loadings in different directions, so combined loadings, so if we have significant loadings in more than one direction, then instead of a yield point, you now need a yield criterion. And just to give you some example of well-known yield criteria, you may have heard of the Prenscia or von Mises yield criteria. So if we plot sigma 1 and sigma 2 to two principal stresses, and we look for the locus of points representing each yield criteria, the dashed red ellipse here is the von Mises yield criteria, which is probably the most widely used one. And it gives a pretty good fit to the yield for many ductile materials. But not all. So if you look at a cast iron, a cast iron, because it's an inhomogeneous material full of graphite flakes, actually it's more controlled by the maximum stress, and so von Mises yield criterion is not particularly good. Okay, so let's move on to composites. So composites lamina are a little bit different. First of all, they are in general more brittle, so they behave rather linearly up to the point where they break, and they also behave differently in tension and compression, and they're also highly anisotropic. We can simplify little things a little bit if we choose a coordinate system to look at them, which is lined up with the fibre directions. So if I consider a unidirectional material, if I set my one direction as being parallel to the fibres and two direction as being transverse, then that simplifies things a lot, and the elastic properties become orthotropic in that coordinate system. So we can then test such a material to find properties such as stiffness and strength, say in two directions, and we'll see that such a material will typically behave fairly linearly up to the point where it breaks. If you do some basic tests on that material, then what you will find is you will find these 4 points, which represent the tensile and compressive strengths in the 1 and 2 directions, that is in the fibre and transverse directions. And if we also tested at a variety of other different stress ratios, combinations of those loads, then what would happen is we would build up a failure envelope. In this case, it looks roughly elliptical, and we can define some kind of mathematical function which gives a reasonable fit to that envelope, and that mathematical function, as defined here, a function of the two stresses being equal to 1, that is what we call a failure criterion. So a failure criterion is simply a function, f of sigma 1 and sigma 2 equals to 1. It gives a reasonable fit through the experimental failure envelope. That was just for two stresses. If we want to include shear, then what happens is we'll now add a third dimension to our to our failure criterion. It will become a 3D surface. If you want to consider a three-dimensional stress state, so that's including the out-of-plane stress, sigma 3, and the shear 1, 3, and 2, 3 stresses, then the failure envelope unfortunately becomes 6-dimensional, and sketching that is beyond my artistic capabilities, I'm afraid. But the maths is similar. Okay, so the situation with failure criteria, I have to say, is not entirely satisfactory. There are a whole bunch of failure criteria that you can find in the literature. There's non-interactive criteria, where each component is assessed independently. You've got partially interactive criteria, which make a distinction between fibre-dominated and matrix-dominated failure. Then you've got fully interactive ones like the SciWoo, which don't make any distinction. All that these are doing is they're providing you with some kind of function that tries to fit the data. As you can see, here's an experimental envelope. The max stress doesn't fit this one very well. Sci-Hill's a bit better. Hoffman maybe a bit worse. SciWoo looks a bit better. Franklin Marin, all that looks great. So there's a whole bunch of possible failure criteria in there, and they're all different. They can't all be right. It's actually which of those is best is going to be material dependent, depends on the system that your material system that you're dealing with. The other thing I'd say is that these are applied failure criteria, and the fact that you've got a failure of applied doesn't necessarily mean that your structure's broken. So for instance, in UD materials, laminae that have some transverse load may crack at quite low levels without significantly weakening the structure. They just shed a little bit of load to the layers that are loaded in a strong direction. So if you're using these kind of criteria, you need to apply some common sense and maybe use a partially interactive criterion that allows you to distinguish between matrix and fibre failure. Okay, so the other thing we can do is, as well as calculating a value of a criterion, sometimes some of the criteria are non-linear in nature, so it can be easier to express what you find out in the shape of a safety factor or a margin of safety. Typical application for this sort of thing might be a structure. So here's an example. This is a side stay fitting developed by Airbus, part of a project, and this is assessed using a 3D version of the Tsai-Hill criterion. So basically, you need to look at all the cases that are loading cases that are possible on the landing gear, and you're really searching for the worst case and seeing whether you're likely to exceed the failure criterion or what your safety factor is. So it's a way of assessing the criticality of the stresses. Okay, so let's move on a little bit and talk about fatigue. There are a number of different ways of approaching the issue of fatigue in laminates, and I'm going to summarize it very briefly in 4 categories. The first, the most complicated, is the one on the left, which is a mechanistic approach where we try and model in detail the physical process of damage. So this example here is a simulation of the growth of fatigue damage in an open hull test specimen. To do this, you need various damage variables and cohesive zone elements, and you have to calibrate all these models and then embed them in the FE solution to track the development of micro cracking and delamination and so on, and the consequent redistribution of stress over time. So they're very nice looking simulations, but very heavy to do, and this kind of thing at this stage is not really practical for applying to real structures. Small coupons such as this is fine. At the other end of the spectrum, and this is where we started, is the simplest approach, and I'm a great believer in using the simplest approach we can get away with. So this is where we started, and this is what we might call a fatigue life approach. This is based on a traditional SN curve approach combined with some of the understanding of composite failure criteria. In between, you have a couple of other options as well, which involve tracking damage variables and seeing how the strength and stiffness of the structure evolves over time. But again, these involve having nonlinear damage models embedded in the finite element solutions. So they're still analytically pretty heavy. So let's look a little bit more at this simple fatigue life approach. So we already talked about static failure criteria. So a static failure criterion allow you to take static strengths in the in the fibre and transverse directions, and also for shear, and based on some assumption you can then have a failure envelope, which is based on your favoured damage criteria, failure criteria. So what we've done initially is to develop a fatigue approach, which is based on the idea that we can extend this to fatigue. I'm not going to go into the details of what we're doing, but essentially, instead of simply having a static tensile and compressive strength, for example, in the fibre directions, we will have a Hague diagram for the fibre direction, a Hague diagram for the transverse direction, and a Hague diagram for shear as well. And The downside of this is that you still need quite a lot of fatigue data to populate these 3 Hague diagrams. Each of these Hague diagrams is constructed by interpolation from 3 SN curves. So typically we will test in tension at R equals 0.1, compression at R equals 10, and at the critical R ratio, which is somewhere in between. Here's an example of a material data set from our database. So this is an example Hague diagram for carbon composite material. So this is now an example of showing this in practice. This is a static failure and fatigue evaluation on a wind turbine blade carried out in nCode DesignLife. What we've done is we've simulated the dynamic response of the blade using a modal superposition approach, and then we've done a static analysis to see where in the time history the most critical loading case is and what the minimum safety factor. We've also done a fatigue calculation. So this has been done. I've carried out this calculation in our in nCode DesignLife, actually in a prototype version. So let's have a look at 1 or 2 of the results in more detail. I'll just pull out 1 or 2 of the pictures. So this is the results of the failure criterion calculation. So if the failure criterion is less than 1, then that indicates that no failure is occurring. If it's greater than 1, then that indicates that we have some possibility of static failure. So what we have here is in this plot, I've just picked out highlighted the result from the most critical elements, and this has a failure criterion of 1.158, so it's a little above 1, indicating that there's some static failure occurring, but it's only in 1 layer of 1 element. So this isn't at all an indication that the structure is likely to fail. It's just an indication that you've got some damage occurring in 1 layer of 1 element. It's also possible to pull out some more details, for instance, in terms of time histories. So what I've done here is I've picked a particular location in the structure, and on the top left-hand plot we have time histories of sigma 1, sigma 2, and of the shear stress at a particular location in the model. That's in material coordinates. And the last time history is actually a time history of the failure criterion. So this allows you to identify at which points during the time history and which combinations of load are giving rise to the most severe loading cases. Another thing we can do is look at the right-hand plot. There's 2 things going on here. There's a cloud of red points, which is outlining the shape of the failure criterion. In this case, it's the Hashin-Rotem static failure criterion, and the blue points represent the loading path at that point. So if those blue points emerged from the envelope, that would indicate that we had a static failure being predicted. So that functionality is all in the software as standard at the moment, so you can get that in it's part of the composite module. What we have also in prototype form is some capability for fatigue evaluation. So this is what I was describing earlier. One thing that's very important here is that we can interrogate the plot and we can see the results for the different layers. And because we've used the Hashin-Rotem criteria, which is a partially interactive criteria, we can distinguish between matrix and fibre failure modes. This is very important for interpretation of the results. So, for example, in this case, you can see that all we're getting is matrix failures. So, unless these matrix failures lead ultimately to delamination and failure in the overall structure, we shouldn't worry too much about them. So we're still working on this and we're developing it in conjunction with a few key customers who are helping us with feedback and suggestions. We're planning to release this as a beta feature for the composite module sometime during 2019. Okay, so we've still got a bit of work to do to refine this approach. So if you use it as a first ply failure approach, particularly for UD materials, it's likely to be conservative. So you can see this if you consider a simple cross-ply laminate. So this is a 090 laminate. If you load this up, in practice, cracking is likely to occur very quickly in the 90-degree layers, but that doesn't really impact the strength of the laminate very much because you still have all the strength of the 0-degree plies. So if you just use a first ply approach, first ply failure approach, you get a very pessimistic prediction. But if you can actually get a very good prediction if you just discount the strength of the 90-degree plies. So you redistribute the load to the 0-degree plies and recalculate, ignoring the matrix dominated failure. Then you actually get a very good simulation. So kind of what you're doing here is you're taking the basic SN approach and you're starting to introduce elements of the residual stiffness and strength modeling approaches. That's kind of the line that we're taking. I should just, before I finish, I'm just going to mention very briefly, we also have some short fibre fatigue composite capability. I haven't had time to talk about that. We've got testing capability for that as well. This is just a very, this is an example from one of our papers and the calibrate examples that we did. It's a vibration fatigue example where we calibrated the fatigue model for the material and then attempted to successfully, as it turns out, to simulate vibration fatigue on a coupon subject to random vibration. Works pretty well so long as you take into account the damping correctly. Okay, so that's we've gone on a little longer than I anticipated, but I'll make some concluding remarks. So just to sum up, composite materials offer massive advantages in the development of lightweight structures, but effective use of these composites requires the ability to manage fatigue durability. So that means managing the durability somehow by a combination of simulation and test. It's a complex problem. Composites are difficult to test and difficult to simulate, but we are working with our customers and partners to develop pragmatic approaches to this, and we'll be releasing software as we think it becomes useful, and also material characterization capability for common material types.